Start a new chapter. Chapter 4. Boltzmann. Okay. And let's start with something simple. Let's start with a discussion of microstates, macrostates, and ignorance. Okay? So, I'm going to play a heads and tails game. I will throw it 10 times. Let's say by some kind of magic, my coins are fair. They are not rigged or anything, but somehow I get 10 heads. Okay? So this configuration, we will call this configuration microstate. Okay? And the number of, so let's say how many heads do I have? I have 10 heads, 0 tails. And this will represent our macrostate. And our ignorance about the system, let's say we are looking at here to the macrostate and we are trying to guess the microstate. Okay? I have 10 heads and 0 tails. Can I guess what happened each time I threw the coin? Yes. There are 10 heads, so each time the person threw, she got heads, and I can guess it 100%. How much ignorance do I have? 0. Okay, my ignorance in this case is 0. Now let's say there is another trial and we happen to have 1 tail, and if I am here, if I'm looking at the microstate itself, I am again 0 ignorant. I mean, my ignorance is 0. I know every microstate. Okay? But that's not the question. The question is, if I'm looking at the macrostate, which came out as 9 heads and 1 tails, what can you say about my ignorance? Has it gone up? It's 10%. Why you are saying 10%? Because it can be one out of 10 times I can be right. I can just guess that, let's say, 6th throw was tails and the rest was heads, and I would be wrong. I can guess 4th was tails and I could be wrong. But I can say that, okay, 7th was tails and I would be spot on, right? So my ignorance is like 9 out of 10, actually. My ignorance is 9 out of 10. I mean, it has gone up. So far, so good? I mean, 9 out of 10 times I'm wrong, right?
Why do you use the probability?
We will come. We will come to a better. Yes.
I mean, you could also be right 9 out of 10 times. Like, why are you wrong 9 out of 10 times? You could be right, so you're wrong 1 out of the 10 times.
9 positions for tails are wrong.
Okay, so it depends on who if you're looking at tails, it depends on the perspective then.
What do you mean?
You're 9 out of 10 times right for heads.
Yes, because if we're looking at heads, then we're
No. We are looking. Okay, I understand your question. We are looking at the whole microstate. So I'm guessing the whole thing, the whole 10 flips. Okay, I'm guessing all of them. And since I see at the macrostate 9 heads, 1 tails, let's say I'm not stupid, and I don't guess like 7 of them were heads and 3 of them were tails. I actually do guess that 9 heads, 1 tails, but I just don't know which one is tails. So does it make sense? I have the same ignorance if it was 9 tails, 1 heads, doesn't matter. Same amount of ignorance. Because this time I don't know which one was heads. Yes? Okay, so far so good. What if it's 8 heads, 2 tails?
10 choose 2 minus 1 over 10 choose 2.
10 choose 2. 10 choose 2 is 10 factorial divided by 8 factorial times 2 factorial, 45. Okay, so there are 45 different scrambles that have 2 tails and 8 heads, and I will be right only once. So my ignorance went up. It's now 44 over 45. Okay? So as what I'm trying to arrive at is that as the number of heads and tails become equal, the number of possibilities in microstates grow exponentially. Okay? So if it's 5 heads, 5 tails, then I have 10 factorial over 5 factorial, 5 factorial. What is this? Are you going to calculate?
Yes.
Yes, just let me know if it's 252 or not. Okay? Thank you very much. Can I continue as you calculate? Will you be able to? Yeah, I think I can. Well, this happens in your exams. Let's say you...
Yes, it's 252.
Excellent. Thank you very much. So, let's say you are in an exam and you have 20 questions and there are A, B, C, and D. And at the end of the exam, you are not sure about like 3 questions and you are suspiciously missing, like there are 5 A's, 5 B's, and 5 D's in your exam. So far there are 2 C's and you were in between. I actually used it in a major exam. It's a good assumption to assume that they will all be equal. And just if you are in between D and C, A and C, B and C in those questions, this data can shift you to move towards having C. Why? Because having the same amount of A, B, C, D covers a lot more space in microstate universe than having 20 A's and none of the others. Does it make sense? Like, if you are doing things randomly, not purposefully, then you end up with these kinds of equal distribution. Okay? Equal probabilities. So, it seems like equal probabilities, this is our take from here, equal probabilities maximize ignorance. In the sense that we meant what ignorance is. Looking at macrostates, trying to guess microstate. Okay, so let me have a parenthesis now. Now we have a parenthesis. We will come back to this problem. In the parenthesis, let me talk to you about Lagrange multipliers. Okay, this is a way of constraint optimization. Constraint optimization. I will give a very simple example. Let's say you have a wire of length A and you want to make it into a rectangle. X on this side, Y on this side. And you are wondering what X and Y would maximize the area. So the area is X times Y, right? So you want to maximize area, you want to maximize X times Y, but you have a constraint. You can't just put X to infinity, Y to infinity. X plus Y has to be, actually, X plus Y has to be A over 2, right? Does it make sense? In other words, 2X plus 2Y is A. Now, how do you do that? Well, you define a function. You first of all write this constraint as an equation equals to 0. First of all, you do that. Then you write something called, I don't know what it's called actually, Lagrange function. What is it called? Lagrangian. Nice. You write down a Lagrangian which looks like this. Your function that you want to maximize, okay, minus the Lagrange multiplier, lambda, times x plus y minus a over 2. This is your function, okay? And look what happens. If I do del L over del lambda, okay, equals to 0, it just gives me back x plus y minus a over 2 equals to 0. So you are creating a function which, when you take the derivative in the direction of the multiplier, you get the constraint, okay? But what happens if you take the derivative with respect to x? You get y minus lambda equals 0. Do you agree with that? Just check my algebra, please. Is this correct? Yes? How about when you take with respect to y? You get x minus lambda equals 0. Well, this tells you that y is lambda and x is lambda, right? So it just simply tells you that both of them are lambda, so you can just write lambda plus lambda must be a over 2, so lambda must be a over 4. And this simply tells you that the way that you can maximize the area is to basically build a square. Are you happy? Any questions? Comments? No? Okay. Okay, so what? So let's come back to our problem. Let me just show it to you this way. If you remember, we said that equal probability maximizes ignorance, right? Let me give you another example, a computational example. We are going to play a flipping game. Let's say I have this time, just like you have 20 questions, I have n states, okay? They all start at 0, okay? And then I pick them randomly and flip them to out of m possible states, like let's say m is 9. So I pick one of them. They all started at 0. I pick one of them and change its number to something between 0 and 8. Then I go to the other one change its number to something between 0 and 8. Where do you expect this will go? What will happen to the system as I run through this simulation? What do you expect to get? Oh, you are so not awake. So, sure. I have 100 states. Let's make it simple. All of them are 0, and I just land on one of them randomly and change its number to either 0 or 1. Okay? 0, 1, 0, 1, 1, 1, 0. Sometimes 1 remains 1, sometimes 0 remains 0. Sometimes 0 goes to 1. I mean, it's fair. Like flipping to 0 and flipping to 1 are equal amount. So what will happen to this system? I mean, what will I observe if I'm looking at the macro state? I start with 100 zeros and 0 ones, right?
Is it Gaussian function?
It's just like 50% of the time it goes to 0, 50% of the time it goes to 1. Okay? They equal separation, but it will fluctuate there, right? Can it go down to 100 zeros again? Very low probability. There is such a probability, but very low. So let's try it actually. So this is our flipping game. So I have number of states is these are. Should I call it number of samples? Just names it after number of classes. Does it make sense? You don't like that? Let me just. You understand what's going on, right? Let's see. Number of iterations. That's a good. M is like when it's 2, it's either 0 or 1. When it's 3, it's 0, 1, or 2. So let's go with 5. It's either it flips to either 0, 1, 2, 3, or 4. So look, for t in range t, just going over all the iterations. It was not intentional, just reminded me. I land on one of those things. I change it to random number that I have chosen. And what do I do here? I just keep the sum. I keep the macro state in B. Did you follow this code or not? Should I make it even bigger? I have just 2 codes today, so we can spend all the time in the world with this code. What do you think about this code? Any questions? Yes.
What's the purpose of summation?
Yes. The summation is telling you, so basically it's summing over M. So for example, it says that how many A's are equal to 0? How many A's are equal to 1? How many A's are equal to 2? Okay, let me just run it. It will run really fast. This is what you get. So we start with 1,000 of zeros, okay? But then it quickly, because when it's 1,000 of zeros, there is much higher probability of landing on 0 and changing it. Do you see? So it quickly gets erased, and eventually we land on the equal probability state. In terms of macro state, micro state is just like a soup going on like that, but macro state seems to be converging at something stable. How are we doing so far? Yeah, good. So it seems like systems go towards this maximum ignorance state. Okay. Now I want to go back. Yes.
So top like the decaying curve showing that okay we are decreasing zeros from 1000 then equal probability. But what about the down?
Yeah. Very good. So there are 0 ones at the beginning, right? So every time you land on 0, there is a 25% chance that you will get 1, and you will add a new 1 to non-existent ones. You know, there are no 1s, no 2s, no 3s, no 4s at the beginning. Every time I come, 25% of the time I don't change 0, so it remains. But otherwise, it becomes either 1, 2, 3, or 4.
These are those 25%.
Yes. Eventually, it enters into a state where all of them are equal probability.
Are fits exponential or like is there more complex function?
I don't know. Probably exponential. Yes, probably exponential. I didn't do any fits, but let me repeat myself. Probably exponential. Yes?
Why did it converge to 1?
Because there are 5 possible states and 1,000 cells. Okay, good. 1,000 divided by 5 is 200. So let's do another thing, like just 2. Did it run? Oh, before it didn't even run. It's just from yesterday. Now it's running. It's just waking up.
Like us.
Yeah, exactly. Do you see what happened now? So when it's 0 and 1, they have converged to 500. But there are fluctuations. You don't expect to stay at 500 and 500 because you keep changing the system, right? There are fluctuations, and some of the fluctuations will actually be large. So, for example, if I do it of course, this is a very bad way of getting random numbers, each time calling a function to just get one random number, but whatever. I mean, do you see the fluctuations? Sometimes it gets unlikely one on one side. So sometimes zeros win, sometimes ones win, but otherwise it just remains there, right? Yes?
Can we run the code twice?
Sure. What do you expect?
I just want to see if there is any change in the distribution of the...
Do you see that there is a change? Did you have a memory of the previous one? There were like 2 ones here. Good? Very good. So, I hope you are with me. Yes? Good. Now, I want to find an ignorance function. I haven't found it yet. Let's say I'm looking for an ignorance function. That depends on probability of ith state. Okay? There are multiple states. It can be 0, it can be 1, 2, 3, 4, 5. And we have P0, P2, P1, P3, etc. So I'm looking for an ignorance function, and my total ignorance, or total or weighted my total ignorance or weighted ignorance will be probability of being at that state times the function of ignorance. Do you buy it? Let's say for every probability, there is a function that takes me from probability to the amount of ignorance. Yes? And then being at a certain state has a probability of pi, and pi times that function gives me weighted average of the ignorance. Now, what I want to do is maximize this one, okay, with constraint of what should be the constraint here? Yes, the sum of the probabilities is 1, right? This is our constraint. We have another mission here. We want to find such a function fpi that maximizes this thing when pi's are equal. Do you see our aim? Because we have looked at nature. And by nature, I mean we have looked at the computational universe, right? We just played a flipping game, and we saw that our ignorance maximizes, or the system goes towards somewhere where probabilities are equal. Okay? We are wondering how can we quantify that state. So hopefully we will get something. We will call it later something. You know what we will call it, but let's call it ignorance for now. We will find ignorance, and it will define the system. And as the time goes, ignorance will start from 0 sometimes. It will maximize. No matter where you start, the ignorance will maximize. Okay? But we first need to find that function. We don't have the function yet. So let's maximize it. What is our Lagrangian? Our Lagrangian is
Sigma pi fpi minus lambda sigma pi minus 1.
Do you all agree with this? Yes? Now, what if I take the derivative with respect to any of the pi's? Okay? What do I get? I get derivative of pi, which is 1, times fpi, okay? And plus, right? Pi times del f pi over del pi minus lambda. So far, so good? Did you follow this? Are you sure? Why disappearing? Because I'm taking the derivative with respect to only one of the pi's. Yes? The others go away. Very good question. And with respect to all of these, it should be 0. Okay? Now, do you remember our second aim? The second aim was finding such a function, fpi, that maximizes this thing when pi's are equal. So I will just pull another trick from my bag now, okay? And we'll ask you, wouldn't it be the case if this was a constant? So if this is a constant, then fpi is equal to a constant. Then all pi's have the same value. Did you get it? Sure. Let's say this is a constant. Only this term is a constant. So this is also a constant. So this whole thing becomes a constant. then it means that this has the same value no matter what pi is, which, since it's a function, and let's say it's a well-behaving one-to-one function, if every fpi is the same value, then every pi is the same value. You can't tell this for any function, right? But our function will be such a function anyways, okay? Sometimes functions do this, right? Then for a certain fpi, you have different pi's. You can have different roots. But this function will not be one of those functions. It will be just this. Okay, so a trick. I'm making this a constant. Still with me?
Yeah.
Yes? So let's then move on. If you buy this trick, then pi del fpi over del pi is a constant c. Then del f is c times del pi over over pi. Take the integral. F is c times log of pi, or ln of pi. Are you happy? Some of you are really happy for some reason. Very good. So our function that would maximize ignorance, that gets maximized when probabilities are equal, is just log of p times a constant. Okay? Now, that constant must be negative if you want to maximize it. Okay? Because log of pi is already a negative number. Remember,
Going to entropy from here?
we are there already.
Is very much that.
Huh? Ignorance is entropy, yes.
Yeah, because you just made the constant negative. What else? Entropy we are getting.
Yeah, exactly. So, just let's take c to be minus 1, and your ignorance becomes pi times log. Should I go with ln or log? Which one do you like? Lots of ln fans. With a minus. So we chose this one, and now it should be familiar to some of you. This is just the information theoretic definition of entropy. Okay? Just choose C to be minus KB, and you get the thermodynamic entropy, right? Boltzmann KB. Okay, let's now talk about entropy. Entropy is ignorance. And ignorance is bliss, so entropy is bliss. Anyways, and the thing that we were talking about all along about ignorance, I was just not giving away that word entropy, because entropy carries a weight with it, okay? Weight. Some people look at it as goddamn thermodynamic quantity that came out of nowhere for no reason, and it's all over the places. Some people think that they do understand it. Anyways, there are many different approaches to entropy, and I like the microscopic approach. There is a macroscopic approach whereby none of this is present. It's just S is del Q over T for some reason. That's how it began. That's how it was initially defined by Clausius, right? But then Boltzmann realized that there is a way of coming to the same conclusions starting from the computational universe. Like there are nothing there's just pure numbers, maybe some balls hitting each other, etc. But you can arrive and describe all the macroscopic things that are going on. You sort of derive everything that has been defined up to that point ab initio, starting from nothing. Initial ab initio, what does it mean? Like from the beginning. From the beginning. You start from the beginning. Beginning is 1, 2, 3, 4, 5. Okay? Good. There are many quotes that talk about entropy and its second law correspondence and saying that, all other physical laws can be proved wrong, blah, 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 not entropy. Indeed, it has its roots in mathematics more than anything else in physics. Okay? Does it make sense? Good. We can go back and calculate the entropy of these systems, for example. What is the entropy here? So you have P heads is 1, P tails is 0. What do we do with 0 log 0? 0 ln 0, it's 0. Because this one goes to 0 way faster than this one goes to minus infinity. Does it make sense? So that's why if you sum all this, like there's only one term indeed, there's minus 1 ln 1, which is 0. So the entropy, 0 ignorance, 0 entropy. Okay? How about this one? What is S here? Well, S is minus 1 over 10 ln 1 over 10 minus, shouldn't have this, minus 9 over 10 ln 9 over 10. And did I calculate it before? Let me see. I did, and it comes out 0.325. So entropy has increased, right? And our ignorance also increased. Remember? 5 heads, 5 tails. Yes. Yeah. I always think that you have a question when you do that. For this one, it comes out at 0.6931.
Precisely about 2.
Say it again.
Precisely natural logarithm of 2.
Natural logarithm of 2. It's also my son's school number. Very nice. I should tell him that he will be really happy. All right. So far, so good? Now, so far, we looked at the case I hope you are not bored. No? So far, we have looked at the case where it's really, we are not constraining the system. We are just flipping the states without any constraint. Can I flip to 4? Yes, you can. Can I flip to 3? Yes, you can. Everything is allowed, so everything goes to the same equal amount. But what if we are dealing with, what did I call it here? Elastic balls in a box. Okay? Let's talk about elastic balls in a box. In a box. So what's happening here? You have a bunch of perfectly elastic balls inside the box. They are all equal size. Don't mind me plotting them differently. They hit each other. So every time they hit each other, what happens is that this one had E1 energy, kinetic energy. This one had E2. Okay, you can now think of this. You can now think of this. This is my energy axis, okay, and this is my probability axis. What is the probability of being over here? Let's say there are 7 particles there, 7 billion, whatever. I mean, 8 billion, no, also 7. Like it's a distribution. Do you get this distribution? Well, when they hit each other, so when there is a particle from E1 and E2 hitting each other, they will be taken out of that distribution and placed in different places, right? They might share their energies. Maybe one will just stop. Sometimes, for example, a ball stops, another ball perfectly collides, and this one stops and this one just goes away. I mean, there are different things. But there is a constraint now. The constraint is that you cannot reshuffle them to any place you want. Once they get reshuffled, E1 prime and E2 prime, okay, for example, this cannot happen because E1 plus E2 needs to be E1 prime plus E2 prime. And as you can see, what I did here is that I increased both of their energies. So this cannot happen. The energy has to be conserved. Are you with me? So that's why there is a constraint here now. Then let's figure out what will.
Are we going to deal with inelastic balls?
No, I will not. But why did you ask?
Then energy is not conserved.
Ah, okay, I see. Very good question. Excellent question. Has everything to do with entropy. In the microscopic world, there are no inelastic balls. And I should explain, right? When we say inelastic ball, we are already talking about 10 to the 23 particles, okay? And they collide, 10 to the 23 here, 10 times 10 to the 23 here, something like that, right? And we say it was inelastic. Well, what happened is that their mechanical energy, some of their mechanical energy, maybe most of it, turned into heat. But if you are following every 11 times 10 to the 23 particle there is no loss. I mean, the energies are reshuffled, okay, but there is no loss there, okay? Because we are now counting the heat. Heat is also included in their motion, okay? This is a very deep, very we will talk about it for a long time. So we will come back to this reversibility, irreversibility issues, etc. But very good point. Downstairs in our perfect box, perfect balls, everything is elastic. Let me just, it's in a computer. Look. Oops. Okay. I have to change this to something that will accumulate. I think this one will take care of that. This is what we are dealing with. I will describe the code next lesson. This is what we have. I hope you are happy. Okay. Let me go back here. 5 more minutes and you are good to go. Now, this time, let me think. What will happen Well, the claim here, we are outstretching our definition now to more constrained systems. We started with no constraints. The function that was maximizing the ignorance while keeping the probabilities equal, we will still use the same definition for entropy. So we are going to claim that even under this constraint, the thing that will be maximized is still something that we call entropy. So we are trying to maximize S, which is Pi ln Pi. Okay? But by Pi, I mean probability of being at energy EI. Okay? Think of it as energies being separated into bars, E1, E2, E3, E4, and these are the probabilities. Now, do we have, so let me give you one of the constraints. We have to have this one sum up to 1. Okay? But we have a new constraint now. Can you tell me what it is? Yeah, very good. So probability of being at energy I times that energy should be average energy, and it should be conserved. Okay, because average energy times the number of particles is conserved, total energy is conserved, so average energy is conserved. Are you with me? Yes. Now our Lagrangian looks like this. We have our function I Pi ln Pi. We have minus alpha times Pi minus 1 and minus beta times Pi EI minus average energy. So I just put this constraint in this form, Pi EI minus E prime, E average should be 0. Amna, is it okay? You look scared. Well, maybe the confusing thing here is that we have two Lagrange multipliers now. Not just one Lagrange multiplier for one constraint, but two Lagrange multipliers for two constraints. Okay? Very good. Now let's take the derivative. Let's take the derivative. And what I get is, I'm just going to write it down over here. Okay, these ones are negative. Can you please check whether I'm doing the right thing or not? So this thing should be 0, right? ln Pi should be minus 1 minus alpha minus beta e to the I. Pi should be e to the minus 1 minus alpha times e to the minus beta times e to the I. Okay? So it's no longer equal. This time it depends on energy, right? What is it is telling you, so this is a constant. This is a constant that you can derive from normalization, whatever. What it is telling you is that Pi's probability of being at a certain energy is proportional to e to the minus beta times EI. Later on, we will not show this, but we know that this is 1 over kBT. So this is just proving Boltzmann's relationship in a very general sense, that this is the case. Okay? Just give me just 1 minute to show you that as this runs, I will describe the code later on, but as this runs, I'm keeping the tab of all the energies, all the kinetic energies, and I'm going to plot a histogram here, not me. And you can see that the thing that I get with the bars is the numerical calculation. They are just hitting each other. It's ab initio. It's not the real world. It's a mathematical universe, but it still fits perfectly to Boltzmann's distribution. Okay, so it's coming from down there to up here. Okay, let's stop here, and I will describe more details next time.